Hello and welcome to Algebra 2. Today is Monday, August 31st. We're going to write this at the top of our page. Our topic for the day is difference of squares. We're going to start with some vocab today. All these words that we're about to list are synonyms for solve. So if you see these words, they all mean the same thing as solve the polynomial. And we'll talk about where they come from in a second. We have zeros, roots, x-intercepts, and solutions. Okay. To think about where these three came from, we're going to consider a graph. If we graph one of our polynomials that we factor, it looks something like this. These guys right here are the x-intercepts. Let's label them as -1, 0, and 1, 0. So right off the bat, you can see where x-intercept comes from. And it is a solution because when you have an x-intercept, this y value is always 0. So that's where zeros comes from. It means the y value is 0, and then root is a synonym for 0. All right, let's kick off our first example. Go ahead and pause and write down the original problem. This down here will be example 2. Okay. First things first, it says find the roots. Well, we know that root is a synonym for solution. So we know that this wants us to find solution. Now, in order to find a solution, everything must equal 0 first. That's where this y equaling 0 here comes into play. So we're going to write that out. Everything must equal 0 first. Okay, I'm going to rewrite our original problem. For everything to equal 0, we need to get it all to the same side. We like to keep this x squared positive. That makes our life easier. So we're going to move everything over to it. 2x squared minus x. Remember, x squared and x do not combine. They're two different terms. Now I'll take away the 6. And we end up with 2x squared minus x minus 6 equals 0. Great. This looks like something we know how to solve now. We know that we're solving it because we saw the word roots. We moved everything to one side. We're now ready to solve. This is an a does not equal 1 factoring strategy because a is 2. First thing I want to do is multiply my 2 and 6. I get -12. My factors of 12 are 1 and 12, 2 and 6, and 3 and 4. I'm going to draw my x. I've got -12 up top, -1 on the bottom. How can we get there? With -4 and +3. I definitely need a box because a does not equal 1. I'll color code our box. That's a 2. All right, in the top left, the green, that's always 2x squared. I can take out 2x and x. And then in blue, I need to strategically pick a number here. Question we ask ourselves is who divides nicely into 2? That is definitely 4 and not 3. I'll put my -4x here, plus 3x here. 2x times what is -4x? That's going to be -2. X times what is +3x? That's going to be positive 3. I multiply in, I have negative 6 in the corner. This number matches this number. Great, that means I'm on track. So my factors are these guys. These are each called factors. 2x plus 3 is a factor. X minus 2 is a factor. But our instructions were not factor, they were find the roots. Roots mean solutions. So in order to solve, I set factors equal to 0. Let's write that. To solve, or to find solutions, we set factors equal to 0. Here's what that looks like. We'll take our first guy here. I'm going to say 2x plus 3 equals 0. Take away the 3. 2x equals negative 3. Divide the 2. X is negative 3 halves. That is one solution. Our second solution, x minus 2 equals 0. I add the 2, so x is positive 2. My two solutions are negative 3 halves and positive 2. Pause here if you need to catch up. Example 2. This is an example of our new topic. This factoring strategy is called difference of squares. Let's think about where this term comes from. Difference is a synonym for subtraction. So there always needs to be a minus sign. This never works if you're adding. Difference of squares, this square means that, first off, we got the x squared, and it also means that this 81 is a perfect square. Perfect squares are like 9, 16, 25, 3 squared, 4 squared, 5 squared. Whenever you square a whole number, you have a perfect square. So we're going to say perfect squares. To further explain what I mean, I'm going to make a list of examples of perfect squares. Of perfect squares. So 2 squared is 4 is a perfect square, 3 squared, 9 is a perfect squared, 4 squared, 16 is the perfect squared, and so on and so forth. Pause here if you need. Great. So the way we factor these is actually pretty straightforward. I take the square root of each term. My square root of x squared is x. We don't carry the minus sign. My square root of 81 is 9. And then I just build them out like this. And our answer is going to be x plus 9, x minus 9. Let me show you why this pattern works. If I multiply x plus 9 and x minus 9 back together, watch what happens. I have x squared, negative 9x, positive 9x, negative 81. These two terms cancel each other out. When we do alternating plus minus, we get two terms that cancel out, and you're back to you're back to x squared minus 81. So this is a good way to check yourself, and it's also the reason we use alternating plus and minus. Pause here if you need. Always remember, you can pause anywhere. You don't just have to wait for me to say pause. I got one last example for you guys. We're going to call this guy example 3. I first always identify your factoring strategy. Our strategy here is difference of squares. I know that because here's my difference, my subtraction. Here's a square. 9's a perfect square because 3 squared. And 36 is also a perfect square because it comes from 6 squared. So I take the square root of each term. the square root of 9b squared, you square root them individually, so it comes out to 3b. By that I mean square root the 9, then square root the b squared. We got square root 36 is just 6. We plug this into our plus minus, and we get 3b plus 6, 3b minus 6. Great, that's all for today, guys. Thanks.